My name is Jose Manuel Pereiras. I am the Territory Technical Manager for the Andean region. So let's start with the agenda. Defining large structures simulation challenges, flow simulation in large structure and construction, standard analysis. This is what I call the first steps to do analysis in large structure, linear, frequency, and buckling. To go deeper, we're going to see advanced analysis, dynamic, nonlinear, and 2D simulation. Large mechanisms, foundation structures. We don't have to forget foundations. Conclusion and answer, question and answers. So, define large structure. We can define large structure as a structure which is much bigger than the human scale, right? This to be sure what a large structure is. Some example, we can have a plant structure. This is very common to use weldment. Also, another example, oil and gas platforms. In this case, we have weldment, but also we have concrete structure, we have piping, we have connection. And of course, bridges and dams. Here we have different material, right? Like steel, concrete, rubber maybe. So, let's see the basics to build a finite element analysis. We need four factors, right? 4 components. First of all, geometrical model. The second one, loads, boundary conditions, and material. Those 4 parameters or those 4 components will produce challenges in large structure. We have those components in every finite element model, right? But for large structure, we have challenges. Different challenges. And I think they are more difficult than, for example, when we analyze a machine. From the geometrical point of view, we have performance. This is because we may have many components in a large structure. If we think about the weldment of the plant structure, we may have a lot of degree of freedom to solve. Size limits, I don't know if anybody tries to run a 1 kilometer analysis of the structure. I did, and we have some challenges in that. I will show you. Large simplification in order to idealize the model. We always have to do simplification, assumptions, in order to get the numerical problem. And finally, some modeling. I will show you some modeling technique that is not in the manual, in the training manual, and is very useful to get, of course the training guys show this technique, but that technique is very useful to get stresses on the joint, forces on the beam. Materials. Large structures may have different material. Steel, concrete, soil, wood, they are maybe those materials that are in every large structure. And those material regards to different failure criteria. I don't know if it is clear. For example, if we are working with the steel, we have to see furnaces. If we are working with concrete, we have to see, for example, it's a frictional model, but we have to see, for example, principal stress. If we see furnaces, it's wrong, right? So different material, we have the same result, but some result is useful and the other is not useful. The same for soil and wood. Loads. We may have fluid structure interaction, like the wind acting on the structure, soil structure interaction, load that they go from the static to dynamics, yes? And finally, boundary conditions. You see the four components. And boundary condition, we may have fixed, movable, or elastic and plastic in foundations. Many of you may know this example. This is the Tacoma Bridge, made in 1940. This is the fluid structure interaction. The wind acts on the bridge, and the bridge starts oscillating in the natural frequency, in the torsional natural frequency. So we have here different materials, like concrete panels, steel cables, all of them acting in the same time. So that is very challenging to simulate it. What analysis we can perform in this example? So maybe frequency, natural frequency, buckling, dynamic response, of course. If we want to go further, we can run post-mortem analysis. Unfortunately, this bridge failed. Like permanent deformation, non-linear behavior, or failure. So we don't want to go up to this stage, right? So the basic concept in simulation, we have to start with our real model. After this, we idealize the problem, making assumptions. We get the numerical result, and with this numerical result, we come back to the real world and try to understand the real world problem. So the assumption will cut some results, but we have to make sure that our assumption allow us to understand the real problem, right? Some basics in simulation. This is a solid model where the 3 dimensions are important. So in SolidWorks simulation, we have 2 types of solid elements. We are going to use, in the session, we are going to use all the elements that SolidWorks simulation presents. So it's important to understand what these elements are. We have the 4-node tetrahedral element and the 8-node tetrahedral element. In other words, we have a draft element and a high-quality element. Many of you may ask, okay, when I use one, when I use the other. I use the draft element. Anybody is using this element for any example?
I need a lot of elements. I don't need the curvature.
Okay. The draft element is useful to get a quick result. I need a quick result, so I need to run faster. That's the reason why I use the draft element. I use a high quality element in order to get a refined result and the final report, and to be sure that the result I'm getting, they are okay. Something similar happens with sheet metals or shells in general. I have 2 elements, the draft and the high quality, 3 and 6 node. This is the shell element. And finally, the most usual element used in large structure is the beam element. We are going to focus, in many cases of this session, we are going to focus on the beam element because it's important, and we have new capabilities in SolidWorks 2011. And now, 2D simulation. Wow. This is SolidWorks 2011, allow us to simulate in 2D, thanks God. So, with 2D simulation, we can simulate, for example, large construction like tunnels. We can go to the oil and gas market for pipes, connection designs. We are going to see some real examples about this. In energy, pressure vessel and heaters. And finally, in buildings, we can simulate frames, like concrete, steel frames, something like that. Okay, this is my first example. I will try to do everything in this example. This is the Wellman structure. First of all, I have to analyze the wind acting on the building in order to understand what the real pressures are. I know that in every region we have standards that may suggest a pressure on the building, but when we are in a region that is not in the standard, or the shape of the building is not in the standard, it's adjustable that we have to run a flow analysis. After this, we are going to see static for gravity, snow, and equipment. We have to analyze. We have to use static, frequency, buckling, nonlinear, and motion. Everybody know what is that frequency and buckling. Okay, I'll show you. Please let me know if you have any question anytime. Finally, advanced analysis like impact, earthquake, and equipment. You see, this is large structure. We have a lot of challenges, a lot of low condition and boundary conditions. Let's start with setting a flow simulation analysis. My objective here is to get the forces on the structure. So, what I'm using now is the wizard of flow simulation. So the first step is selecting the name. Next, the unit system. It's very straightforward. This wizard is very easy to use. There is not any secret. Right now, this is important because I have to select between internal or external condition. Internal means when I have a pipe and I have to analyze a flow into the pipe. So this is internal. In this case, it's external. Why? Because I have the building and I have the flow acting around the building. So this is external. I select the gas, is air, of course. Doesn't matter what this is. And now I have to introduce the velocity of the air, right? Where we can get this velocity? From where?
From window region.
Yes. No problem. The building code. We have a region information that this information tell us what the velocity is expected. I don't know, in the 10 years, the highest velocity. So this velocity is an input for us. We have to find information, right? In this case, it's 20 meters per second. And finally, I decide this is a selector of the refinement of the mesh. If I go in the red zone, that means that the mesh will be coarse and faster. The analysis will be faster. If I go to the right, the analysis will be slow but more precise. And that's it. What you see now is this black box is the computational domain. That means that into the computational domain, all the calculation will be done. So it's very important to understand how big, in this case, should be the computational domain. Why? Because if it is too small, what's going on? If the computational domain is not big enough. Yes, I will have a boundary condition perturbation, right? So the result, of course, flow will run with any problem, but the result will be rubbish. Yeah? And finally, what is missing is the goals. The goals tell the software, tell flow, what I'm interested on. So in this case, I'm interested on having good pressure field. So I'm running. This model takes around 20 minutes to run. What I get from the model is, first of all, I have the velocity field. This is important in order to see how the velocity is around the building. So I have, if you see, the yellow zone is 20 meters per second. This was my input. And around the building here, in the walls, in front of the walls, I have slow velocity under 20 meters per second. This is expected. And over the building, I have high velocity. What produces this velocity? Pressures. The blue one produce, if the air is here, the blue one produce, we can say, a push pressure, right? And the red one, the velocity produce a pulling force. So this is the result that is very useful to understand, very useful for the analysis. The pressure of the load. And if you see, this is not uniform, this is not trapezoidal, this is a shape that we never imagined. We can get only from flow. Of course, in the standards or in the information from the region, we have a simplification. So, from flow, I got the real pressure distribution. And with this real pressure distribution will be my input in my Wellman structure. If you see, they are non-uniform. So, non-uniform load is a new capability in SolidWorks 2011. Now, in SolidWorks 2011, we can define non-uniform load. I will use this simple example in order to show all the options that we can choose in SolidWorks 2011 with non-uniform load. I take a I-beam with a length of 6 meters and a load of 100 newtons per meter. This is one of the options, the table-driven force. This is the most general option. With this option, I can introduce any force, any shape, like in this case, I will use it. And the three other options are triangular, parabolic, and elliptical. Okay? Yeah.
In the previous slide, how did the pressure resolve itself into the uniform distribution volume? The pressure from resolved into those
Yeah. The pressure is a result, the pressure field, right? So it's a result like the velocity. So what I have to do is only to introduce the input, and this is an output that is calculated.
It takes the weights and multiplies by the pressure and resolves it on the velocity.
The width. This is what I got is the field pressure. What I can do is to take in flow, there is an option that I can take a surface and I can run an integration of the force. So it helped me to understand what the real pressure distribution is. But this, we don't have a button that click, and no, unfortunately, it could be a good enhancement.
Do you know what happens if you attempt to use the option that you import pressure loads from flow? If you use that explanation,
the problem here is actually this is not a solid, right? It works for a solid, but in this case, if you see, look at this. This is the actual building, right? With the sheet metal. So the flow is acting on the sheet metal, and the easiest way to do that is to integrate the force and to go directly to the weldment. I think if you put all the conditions with the sheet metal and you analyze everything, you can get the forces, but I didn't try it. But it could work. So in the property manager, we have for this option, remember, table-driven force is the most general, and we have the other one, triangular, parabolic, and elliptical. So if we use a triangular, parabolic, or elliptical, we can choose this option. This is a total load distribution or center load distribution. We are going to see how they work. And finally, for a table-driven load distribution, we have to choose this one, and two columns appear. The first column is the percentage of the distance, and the second columns are the actual values of the force in Newton per meter, right? So let's see the triangular law. This work for triangular, parabolic, or elliptical, right? If we use Q equal 100 newtons as an input, the resultant is 100 newtons. So the resultant, although the shape of the law is triangular, the resultant, of course, will be in the middle of the beam, and it will be 100 newtons. On the other side, we have the center law option in SolidWorks simulation. The value is the same, 100, but the distribution is Newton per meter. So if we do some calculation, the resultant will be this number times L divided by 2. This is 300 newtons. So you have to be very careful with this, because if you choose the wrong option, again the result won't work. I'm doing now a comparison between uniform load we have in SolidWorks 2010 and before, and this is the new option, total load as central load. These are the input in SolidWorks simulation. So now this is who are using this diagram? Sorry? They are the shear forces. The shear forces, yes. The shear forces. These diagrams are very important. I think they are the most important diagrams for everybody who is working with weldment structure, with large structure, with weldment. Why? Because engineers use this diagram to understand the structure very fast. They see, okay, this is the shear force. Okay, in the at the end of the connection, I have 50 newtons. So 50 newtons will be an input for me to simulate, to calculate the joint, right? If you see, for uniform load, this is what we learn in the university, in the first courses. You remember, if we have uniform load, we got linear shear force, and if we have a trapezoidal or triangular force, we got a parabola, a quadratic parabola, right? The difference here is that in the total load option, I got 50 newton because the resultant was 100, and in this case, I got 150 because the resultant was 300. Something similar happened with the bending moment. Actually, the shear forces are mainly used to calculate the joints, and the moments are used to calculate the beam, right? Because in weldment, for example. So, turbine-driven load distribution is not useful now. I cannot use triangular, parabolic, or elliptical. I have to use, in this case, table-driven load distribution. So, this is the input in SolidWorks simulation. As I told you, this is the first column. I'm going to see that. And this is the actual value. So let's see how to set a static analysis, right? This is very basic. The first step to run an analysis in a large structure, a weldment structure.
Do you apply the load only on the vertical? Apply the load only on the vertical?
No, I will apply the load on the columns that are the structural members that are in charge of take the horizontal force, and I will apply the load on the curved beam. Yes, the lifting load. On this way, no, but of course that is called another low stage or low environment, right? Because you have to take into account the other weight of the wind. Yes. So I have to choose the material, the steel. This is really important because this is a really important option in order to select condition for every, if you want, you can choose condition, boundary condition for every bar of the beam. Yes? The red and blue sphere means that you can select rigid or you can release some degree of freedom. This is very general. I don't use too much, but it's important to know. So right now I'm fixing all the boundary conditions at the bottom of the building. I am assuming that the foundation is very rigid. And now I will set the non-uniform load. Yes, you see, these are the three options. As I told you, the triangular, the parabolic, and elliptical option. But in this case, I have to apply a random shape. In some way, a random shape is not triangular. So I will apply this shape, choosing table-driven load distribution. And these are the two columns, right? I have to fill this table. So the first column is the percentage of the percentage of the length of the beam. 0, 25, 50%, 75%, and 100% are the values that I used. And the second column are the value of the actual load in Newton per meter. Is it clear? Okay. And this is the shape. You see, because I got from flow this information, I copied the shape on the column. So again, the red and blue sphere means the end of the column. I can flip if I want. You see. And now this is a pressure acting on the building because it's the wind. And now I have to introduce the lifting force, causing, you remember, because the velocity of the air in the top of the building is higher than the average. And I will choose a parabolic option because it matches with the pressure field, with the field pressure.
Looks like you put the force in the bottom beam, in the lower part of the beam, and not in the top beam. In the whole place of the beam, should I go down?
Actually, the beam is only I will be using the bar element that I showed in the previous slide. So the bar element is a unifilar, is a line element, though it doesn't have faces. So the load is applied on the beam element. So it doesn't matter in this case where the faces are, right?
Because when you have a beam that is about 20 feet high, you show that you're putting the force in the lowest part of the beam. He divides it more than
This is.
Zoom out. He's just saying
This is a video. Sorry.
did not complete the loading of the.
No, yes, because this is an example. If I have to, I have to introduce. Actually, I have to put in the column. I have to put all the three members in the middle, and the load in the other member. Yes, that's right. Yeah. This is only an example to show how to introduce the load, right? Yes, but if we want to run this example with all, we have to take into account that we have two different load stages. What you said, we have this load from the wind in this way, and we have a longitudinal wind also, right? Yeah, this is only an example. Thanks. Of course, I have to include. I don't know I didn't do in this example, but I have to include the load in the others curve beams. And that's it. I run it, and what I get from SolidWorks simulation, first of all, stresses, right? What for? With the stresses, I check the stress of every element, every member of the structure. I compare with the yield stress. If this stress is higher, the actual stress is higher than the yield stress, I have an issue, right? I have to make some decision in order to change it and to get it lower. So stresses, this is static, right? This is the very basic analysis. Stresses. Also, what else? What do you look at? What do you want for a static analysis? Deformation, exactly. Displacement. This is very important for this kind of structure because they are very flexible. And finally, another result, the beam diagrams. Axial forces, shear forces, and bending forces.
How are now in 2011 the beam diagram with this curvature? Because in previous version, if you have curvature, you must get confused because they have only one direction for the beam, and obviously it's
In this case, it's not plotted, but I don't have a. I can get in the same way that I get for the straight beams, I can get the same diagram for the curved beam. We can see after. Okay. But I don't have any problem to see the diagrams. Okay, we already set and analyzed static analysis. For this kind of structure, what other analysis you will run? Buckling, frequencies. Yes? I will show you only frequency, how to set the frequency analysis, because it's easier than the static analysis. I'm interested only on natural frequencies. So, what I need is the model is there. I select frequency. Yes? Frequency analysis. And what I need is material and boundary condition. That's it. The mass of the component is SolidWorks simulation taking into account the mass of the component, because actually what SolidWorks do is discretize the beam in finite element. So every finite element take the mass. Of course. Yes, you have to include, if you have another component, yes, you have to do, in this case is more complex, because you have to include equipment, other forces.
I usually do is I have the walls, and I say, it's beautiful analysis that uses remote mass.
For example, this is another way. So you use a remote mass in order to take into account in the, that's very important. Everybody understand this? Okay. Yes?
Can you do spring stiffnesses for the boundary variable stiffness?
Sorry?
Can you do spring stiffnesses for the boundary?
I will show you. I will show you in the how to replace with the spring. Yes. I will show you. So, the standard studies that we already run is ferrostatic. In this example, I got 2 megapascal. The maximum stress is 2 megapascal. Is smaller than the yield stress, so the static analysis is passed. We ran frequency analysis, and we got from the frequency analysis natural frequencies. It's very usual. I always get almost the same. It's very usual to have more or less natural frequencies around 1 Hertz. Right? In this case, I got a range from 0.6 up to 1.2 Hertz. So what I have to be sure that I have no equipment, for example, in this range. If I don't have equipment in this range, oscillating in this range, so the frequency analysis is okay. About the buckling, Although static and frequency analysis passed, I have some problem with buckling. The two central loads are actually buckling. Yes. How I detect this? With the BLF factor. BLF stands for buckling load factor. And the formula is the critical load divided the applied load. So what happens if the BLF is less than 1? That means that the applied load is higher, is greater than the critical load. So actually it's buckling. What would you do in this case? We have to make decision because we're engineers. Increase section is one option. That's the option that I did. But we have another option.
Modify the geometry of the
Modify the geometry of the structure. We can add some additional bars in order to restrain the column. And finally, we may change the material, but it's not common to change the material, right? So in this case, I enlarge, as you told me, I enlarged the two central columns, and I got the BLF equal 3.4, so it passed the buckling analysis. So the standard analysis are okay. Now we are going deeper. We go to the advanced analysis. Actually, dynamics load. Dynamics load can come from impact, earthquake, or equipment, right? This case is an example. I simulate only an impact load on the curved beam. This, you have here the function. The horizontal axis is time. This happened in a very small quantity of time, right? This is a fraction of a second. This is an impact. It's boom, acting on the curved beam. And the actual values is the value that you expect that this load could get, right? The problem here, I have to run 3 times this model. Why? As I told you in the beginning of the session, what are the components in every finite element model? We have geometry, material, boundary condition, and load. But in dynamics, in large structures, in dynamics, we have the damping. I run with the low damping, and I got almost 10,000 Pascal in one point of the structure. It doesn't matter where it is. I got 10,000 Pascal. With the medium damping in SolidWorks simulations is only a field that we come to put 2 fields, that it doesn't matter what this is now, but we have to put 2 numbers, right? Two magic numbers. The medium damping is 4,000 Pascal, the same structure, the same point, the same load, only changing the damping, and with the high damping, I only get 600 Pascal. So, damping is playing a very important role in the critical. The bad news is that we cannot get the damping from numerical simulation, right? Damping should be taken from the actual structure, and you can tell me, okay, Jose, but I don't have the structure yet. So we have to take the damping from some similar structure, is a test on the structure, right? There is no way to obtain the damping with simulation in this kind of a structure. Okay, let's go to taper beams. What I mean with taper beams are the beams in which the section is not constant, right? So they are used in order to make more economic the construction. So taper beams is a new capability in SolidWorks 2011. We're using this example. This is an example made of frames. Those frames could be made of concrete, wood, maybe steel. I'm interested not only on having forces on the beam. Yes, that we already did this in the Wellman structure. I'm interested on having the field stresses on the joint. So I want to have everything in the same model. So let's define taper beam. Taper beam, because it's a new capability. Taper geometry can be now treated as beam with varying cross-sectional size. People who want the presentation, I can send you, if you at the end of the presentation, I will put my contact information. If you send me an email, I will send to you, yeah? Taper geometry should have to the same cross-sectional profile along the length. In SolidWorks, we are going to see that only is right-click and treat it as beam, because SolidWorks, at the very beginning, SolidWorks simulation understand, okay, this is solid element, but we now have the ability to treat as beam. And this is the geometrical representation and the finite element representation. Bien, some theory. I don't want to go deeper with the theory. I want to show some quick review. The theory of taper beam. Taper beam is replaced. Every finite element of the taper beam is replaced with a uniform finite element with these formulas. These are equivalent formulas. On your right, on your left, you have the equivalent area in this case for the uniform finite element, and on your right you have the areas for the taper, for the actual taper finite element. So these are the cross-sectional moment inertias, and this is the torsion constant. So this is my model. If you see, it is splitted, right? Because, as I told you, I'm interested on having forces on the beam and stresses on the joint. And this is the mesh. You see? Now we have beam elements. They are tapered because you see that they increase. This is a very coarse mesh, right? I can put. Actually, this is not good for an actual analysis. But they are the taper beam elements, and this is the solid element on the joint, because I'm interested on getting the stress result. So this is called what we call submodeling technique. With this submodeling technique, we got beam forces like axial, shear, and bending, and we also get stresses on joints. So let's see how to use this submodeling technique.
How is the joint between the beam and the solid? Because the solid has no degree of rotation.
Yes, sir. I will show you right now. Yeah, this is actually the most critical part of the submodeling technique. And this is the explanation. This is a multi-body part, right? To answer your question, what you see now is a surface, is a dummy surface that we have to include. We must include this surface as the interface between the solid and the beam. At the very beginning, when I ran my first analysis, I didn't do that. So SolidWorks simulation work as well, but the results are not useful. Why? Because if I don't have this rigid surface, the problem is that the beam will produce a rotation only of some nodes of the solid. So what I get actually is a softer model than the real model. Is clear that? Okay. So this is the trick. Put in a rigid surface. I have to, in SolidWorks, right-click, treat as rigid. So it's a static analysis. That's it. I select a static analysis. The material here I had to create a concrete material, what all the YAM modulus, because it's static, the only input that I need is YAM modulus or elastic modulus a Poisson, right? You see, this is the beam. So I right click on the simulation trick. This is right click, treat as beam. That's it. And SolidWorks understand that you want that this solid came into a beam. These are the surfaces, 4 surfaces, because I have 2 joints. I have 2 and 2. So right click, treat as rigid. The yellow spheres are the joint of the beam. Yes, at the end of the beam. So now I have to add a contact condition between the joint of the beam and the rigid surface. Because the rigid surface will be bounded with the solid element, it's not necessary to do anything with the solid element, only with the beam. Of course, I have to do this for every joint that this is in this mixed mesh. At the bottom of the model, of course, I fix the model and I apply some loads in order to get some result. A vertical load acting on the frame. Of course, these frames are useful to get horizontal forces, right? And you see, this is the mesh. This is a mixed mesh. Solid mesh mixed with beam mesh. And this is the result. You see, you have the solid element follow the beam element, right? So this is the submodeling technique. The result that I got from this is, for this load and with this technique, I got the result on the beam element, on the frame, 1.6 millimeter, and on the joint. If you see, it's very useful this, because for civil engineers that work with reinforced concrete, from this analysis, actually this is for misses. This is what I told you that is rubbish. Okay, what we have to do is, for example, principal stresses. Why? In order to get, for example, the plot is very similar. I use axial stresses in order to get the integration of this volume of the stresses, and I get the area of the steel bar, right? So the engineer not only can get the dimension from the beam, they always can dimension the joints. Another standard analysis, static, now frequency. You see the difference between a Weldman and a concrete model, right? The Weldman model, do you remember the frequencies? 1 hertz, more or less, 1-2 hertz are almost the same. In this case, we got the fourth first natural frequencies, 19, 32, 42, and 63 hertz. And these are the shape modes of the frame. The first column is the first and the third mode. They are out of the plane. So if I fix the out of the plane mode, so I will get only the second mode. So this is a way that the engineer could do. For example, if I have an equipment acting in the first mode at 19 hertz, I can fix only this plane, and I go to the second natural frequency, right? Only fixing this mode. Something similar happened with the BLF, with the backlink analysis, and as you see in concrete model, it's not very usual to have problem with backlink, right? This is for Weldman, but in this case I have it's working for backlink, no problem. Now, someone here told me that is working with wood. suppose that this frame is made of wood now. So we have to dimension the joint. To dimension the joint, I will use a new capability, another new capability of SolidWorks 2011, is 2D simulation. 2D simulation allows me to calculate this kind of plate in a very fast way. This is the model of the plate. Yes. I assuming that I already get the shear force. If you see, I select here, this is a static, and I select here, there is a field, I have to check it, and this is 2D simulation. So, in 2D simulation we have three options. The first one is plane stress. The second one is plane strain, and the third one is axis symmetric. The question here is, what of those three I have to choose? Plane stress. Why? Because all the forces are acting on the plane of the plate. Plane strain is useful for what? For example, for tunnels or for pipes, where plane strain means that the deformation in the axial axis is zero. And finally, the axis symmetric I will explain in another slide. So in plane stress, I have to choose the plane to take into account and the width of the plate. Yes.
There is something I'm missing in SolidWorks. You can link these values to the values that you have in the model. Use parameters, so that if you change the model, you don't need to change this thing by hand. So now you are inputting.
Yeah.
When you do a shell, okay, you end up saying which thickness.
Yeah.
Half the thickness in the parameter.
Yeah. Yeah, that's it.
You can do this with CATIA, you can use the parameter of the model to put it into the simulation. Okay, so that when you make a change in the model, you don't miss a change in the simulation.
That's it. I think the reason why we cannot change directly from the model, it could be done. I think it's very, yeah, it's very easy. Yeah, that's very easy. But I think, for example, if this plate, suppose another model that is not the same width in every part, so is slightly different. So you can use a 2D assumption, a plane stress assumption, and in this case, it's not the only one width. Okay, you can choose. Maybe the software can choose the average. Okay, yeah, it could be another enhancement. So I have to decide the plane and the width of the plate, and this is similar that we already done. Material, boundary condition. Now I'm assuming that this is on the column, rigid column. So I'm fixing the 8 holes, and on the other 8 holes I'm putting the shear force that I got from the diagram, right? This is very usual for civil engineers that design joints. They design joints separately from the actual model, right? So this is the mesh is the same. I have the bar that told me what is the refinement, and I ran the analysis. Of course, what I got from the analysis, what is? Stresses. I'm interested on stresses. So if you see in this example, this red arrow show that the stresses around the corner are higher than the yield stress. So this plate is not. We have to optimize this stress. So what do you think? What can I do? Other radius, right? So we come back to the geometrical model, and we have I added a 100 millimeter fillet. I go back to the study and run again. The yield stress is more or less 600 megapascal, and what I get here is 550. So it's a very good design, a very good showing, because it's optimized. So this is almost the same that in 3D, right? And of course, in the assembly, the showing is updated, and the show is done. I will show you now a comparison between 3D. If I want to do this, I can do this in 3D, right? But look at the numbers. For a 3D coarse mesh, I have to use almost 13,000 nodes. And for a 2D, only 1,800. But if I want to get good result, I have to use a refined mesh. So this is ridiculous, right? Imagine for a showing, designing a showing, 123,000 nodes. It takes the whole day to resolve a showing, and this is very fast. 30,000. You have to take into account that when we increase the node, the time that the solver takes is exponential with the number 3, right? It's a cubic exponential. So I don't like to call this 2D simplification. I like to call 2D simulation, because we are faster, more accurate. Let's go to the oil and gas application. We are going to see some pipes, some real customer cases that they are working on. We have a different structure in oil and gas. This is one of our customers that is using a net of pipe in order to conduct oil to the store tank from the oil wells, right? So if you see the size of the model, it is 1.2 kilometers by 0.7. It's really big. So we have to do some assumption in order to run. For example, what we do is to take a sub-assembly and to run this. So this is one of the sub-assembly, the most important sub-assembly. You see the main branch. The main branch is a 2 meters diameter pipe that is collecting the secondary oil well. Yes? Now I'm using a new capability of SolidWorks 2011. It is called, is someone that knows how it's called? Walkthrough. Walkthrough is a new capability, is a CAD capability that allows me to like flying over the structure and see large. This is very useful to see large structure, right? It's like a game. We have the controls, and we can rec the video with the red button. So in this case, the challenge in this case were two. First of all, the size, and the second challenge was the quantity of degree of freedom of the flow. This is a flow simulation. What the customer want to have is the pressure losses in every branch, and the forces active, because you may know that with flow simulation we can get the actual forces acting on the accessories. Yes. This is very important, the gravity, because this is a non-uniform ground, so we can have 30 meters of difference between the end and the two ends of the structure. You are seeing now the pressure field, and this is what the customer is looking for. This is the pressure losses in every branch. Some jump of the pressure happens, and these are the partial pressures, and the total pressure loss is that one. This allows the customer to optimize. Imagine, no, a pipe a pipe of 2 meters diameters with a thick steel with a thick of like a 2 inch. So any optimization that we can do in this is too much money. Really? This is one of my biggest customer. They work with petrochemical mills. This is smaller. This is 1 meter diameter, the pipe, and it's around 100 by 100 meters the installation. So what they work with steam at 150 Celsius degrees. So what they have from flow simulation are forces on accessories, temperature field, and they run what they call this is a very well known in this application, flexibility analysis. In the flexibility analysis of pipe, they focus on stress concentration, displacement, and support optimization. I mean, with support optimization, these are the support optimization, right? Because imagine that you have this pipe and you have to put every 30 meters, you have to put a bracket, a support, in order to allow the pipe going, no? So, at the very beginning, this customer used beam elements because they were very fast and very useful to get the displacement of the structure. But right now they are using shell element, a mixed mesh. This is a shell element mesh with solid element. So what are the advantages of using this? They can get from flow directly. In this case, yes, is direct the importing the loads.
Can you import the loads from flow, which you need to make with solids, import it into a shell?
They do that. They do that. They import not only the load, they get the temperature field.
I can do it only because I run the flow solid. I have to import it into the solid.
Okay.
Not into a shell.
Okay. They are doing this. What is very important for them is that they are getting stress concentration in every part of the pipe. Imagine that each pipe expand and contract every time, right? With the sun, with the steam. It's a very difficult case to be solved. This is another application. Actually, this is you are going to see if you download the exercise from the website of SolidWorks. This is a new exercise in the nonlinear material, in the nonlinear manual, right? But this is actually this comes from a customer. It's not the same model, but it's inspired on a customer. So this is an oil well. What we are focused on now is on the pipe. To go deeper, we are focused on the connection. Imagine that this pipe could have from 2,000 meters up to 5,000 meters. Every 12 meters, we have a connection of that. So what happened in this connection, we have plasticity. We have a nonlinear behavior. So up to now, we already run static, frequency, backlink, dynamics, and now we are going to a nonlinear application. In order to understand nonlinear application, we have stress-strain curves. Yes, everybody is familiar with this. This is stress-strain curves. For a brittle material, we have a very few percentage of a strain. Epsilon is a strain, sigma is a stress. This is a moderately ductile, and this is a ductile material. This material is used in this kind of application. This is the yield stress, and this is in the nose, in the contact of the pin at the box in the connection. this is one of the points that is over the yield stress. So what happens if I unload this point? This is a loaded point, right? Sorry? Permanent deformation, plastic deformation. So if I unload this point, I got plastic deformation. This is, or permanent deformation is the same. This is the name in SolidWorks simulation. The rest of the deformation is elastic deformation, is the recoverable deformation, and this is the total deformation, right? These are the three plots that I can get from SolidWorks simulation. And this is the full scale test. This is a real test. You see, this is an overload connection, and if you see, we have, I get a zoom. These are the steel fiber. This connection is unloaded, and you see the permanent deformation. So this is what in this kind of application they call plastic shear band, because it's a kind of plastic shear band, permanent deformation shear band. And here we have the open seal. This is another problem. This connection have two problems: a structural problem, and the biggest problem is open. What does it mean? What happens if it is open? Sorry? Leaks. We have the oil. Imagine, this is a post-mortem analysis, right? The customer call us and say, the connection phase, I have a chaos in the ocean, leaking oil, and a very nice circle of oil in the ocean, right? So we have to solve this with SolidWorks simulation. The nonlinear state, these are the stages that are the stages for every example in nonlinear, and in SolidWorks simulation we have to we can simulate everyone. First, the linear static. This is what I will be focused on, this material nonlinear. This is the input in SolidWorks simulation, right? We have elastic modulus, Poisson modulus, yield strength, or yield stress, and the tension modulus. This is a bilinear model, right? Many of you can ask, okay, but Jose, I want to get all the curve in my nonlinear analysis. It could be done, but in many cases it is not necessary, because only with a bilinear model is faster, and I get the same result. That's it. If we can go further, we can go the MNO analysis plus large displacement. It is not the case, but it could happen. And what is very weird to see is large strain. Large strain is a theoretical test. It's when, for example, necking. Do you remember in the university when we ran a necking test with the bar and the bar neck? This is large strain, but it's not used. It's not very common to see in the real application. So this is the actual model. We try to run. There is one of the application engineer, but we tried to run in 3D with a 3D model, and it was impossible. It takes a lot of time. It was not stable because the contact, it was impossible to solve the contact. So now we have the new capability, 2D simulation, and the question here, what of those three options is it? Axisymmetric. So in this case, the assumptions are, in order to use the axisymmetric option, cylindrical geometry and axisymmetric loading. So these are the options that I have the assumption. And the challenges here are contact plus material nonlinear. I have contact in the nose between the pin and the box, and performance. As I told you, the 3D approach is impossible. It's impossible in this case. So in order to run an axisymmetric model, I have to have axisymmetric geometry and axisymmetric load. If any of those conditions are not accomplished, I have to go to a 3D. No way. Now I show you how to set axisymmetric analysis. Now I'm cutting only the geometrical model. You see, this is the penetration between the pin and the box. The penetration is so high, so I will have contact stresses and I will have penetration. I will have plastic strain. So this is the challenge, to solve this in the same time. Again, this is a nonlinear study, so I have to go here to the nonlinear modulus. Here I'm selecting the static is a static nonlinear plus the 2D option. Now I'm selecting the axisymmetric here. And here I have to select the cut plane. I have to select what cut plane at one axis. That's all. I can flip the cut section. So what now I'm interested on is getting a good mesh. I will show you how to get a good mesh in this case. So if you see now, this is a good mesh for all the connection, but in the seal area, because I need the contact stresses, I need a very refined mesh. So in order to do that, I have to add what? Control mesh. So it is the same that in 3D mesh. I'm selecting all the edge. You can download again this exercise from SolidWorks website. And the control mesh that I include is 0.07 millimeters. So it's very small, and this is the reason why it was impossible to run in 3D. Imagine in 3D running this is more than millions of degrees of freedom. Impossible, right? So about the material, I created a nonlinear material. We have, in this case, I created my nonlinear material using foam misses, right? Because I am working with a steel, a ductile steel, so I select foam misses. And now the challenge, the biggest challenge to do that. Solving contact with initial penetration material nonlinear present convergency issues. When I said present convergency issue, that it cannot be solved, right? If I have penetration with nonlinear material and I am over the yield stress, getting a lot of plastic strain is almost impossible to be solved. So the trick to do that is first solve the contact under elastic behavior. What does it mean? What you see now here is a dummy function. The axial axis is temperature, and the vertical axis is yield strength. So I'm including a dummy temperature in order to, for very low temperature, I have very high stress. So in this stage, I solve the contact, right, in elastic environment. When the contact are solved, I slowly incorporate the real yield stress. So I warm up my connection with a dummy temperature. I put the expansion coefficient to 0, right, in order not to have any expansion. And the simulation is that I go from the contact resolution to the contact resolution plus plastic strain. So this stage, I got everything in the same time, right? Is it clear, the trick? Okay. And the result, finally, stresses. Of course, they are over the yield stress, but for this industry, for this application, is the bread and butter, right? To have yield stresses. The point here is that the plastic strain doesn't cross the shear band, right? Do you remember the full scale test? I have the shear band. In this case, are the permanent deformation. They are not crossing, so this model can be taken that it's okay. Yeah? This is the approach for nonlinear with plasticity. Another customer working with these concrete molds. They are, of course, large structure. You see the guy here. Did everyone see this kind of molds? These molds are, they close and open. They close in order to go into the tunnel, and they open in order that after they open, they put the concrete over them, right? And this is the way they are constructing the concrete structure. So, the challenge here, of course, we can analyze the weldment structure as we already did, static, frequency, buckling, that's it, and dynamics. But the problem here were get the actual forces of the actuators. They need to get the forces for those actuators. So, what we run is a motion analysis. It's very easy to run because actually this assembly is a three-part assembly, the top part and the two legs. So it's very easy to run. They are considered, all the structure is considered like rigid because we are in motion. And this is the motor. I have to include a motor in every actuator. And this is a new capability in SolidWorks 2011. Another new capability. This is the function builder. The function builder allows us to construct the function of the motor, right? So it's very easy to use. And when we run this analysis, we got the forces. Finally, soil application. That's someone asked me to do that. Soil structure and interaction. In SolidWorks simulation, we can add. This is not fixed. This is not movable. This is elastic behavior. This stiffness of the soil replaces the actual soil, right? So it's very useful for this kind of foundation, for example. These are the results. And of course, we can go deeper with frequency, dynamics, and nonlinear, right? Yes, nonlinear behavior. Finally, for a structured plant and buildings, new capabilities of SolidWorks 2011, beams and 2D simulation. We have taper beams and non-uniform loads, axis symmetric, plane stress and plane strain, flow and HVAC. I use flow here, fluid structure interaction. I didn't talk about HVAC. HVAC is a new module in flow. It's for air conditioning design. It's, of course, for simulation. Walkthrough a grid system. I use walkthrough to visualize my pipes, you remember? Modular structure grid system. These are the two branches here are CAD application, but they are really useful for large structure. Faster performance enhancement in weldment and equation and design automation. The conclusion are analysis of large structure were presented. Different application of type of study were shown. All of those studies were shown. Flow, static motion, frequency buckling, nonlinear and dynamics, and new SolidWorks 2011 capabilities we saw. Beams, non-uniform loads, taper beams, and choose the simulation, axis symmetric plane strain and plane strain. Okay, if you have any question, please let me know. We can discuss now. And you have there my contact information. Everyone who wants this presentation, please send me an email, and I will send you the link to download. Thank you. Gracias.